Hello everyone, my name is Carlo Bailey. Today I'll be talking about our paper, This Room is Too Dark, The Shape is Too Long, Quantifying Architectural Design to Predict Successful Spaces, where we explored the use of machine learning to predict future space utilization. But before I get into that, I'd like to briefly start with this trope that was articulated eloquently by Klaas earlier, that data in the 21st century is to what oil was in the 20th century, meaning that the largest companies of today are extracting their value and their wealth, not from the earth, but from the data that we leave in our digital traces, in our iPhones and in our day-to-day. However, the more lofty claims by some is that this amassing of large amounts of data is what's going to set these companies apart in the coming age of in the coming world dominated by artificial intelligence. And you can think here of the current race of autonomous vehicles between companies like Tesla, Uber, and Waymo. And I start with all of that just to say that this echoes how at WeWork we are starting to think about uses of data, where we have over 1 million square feet in office space, and we collect near real-time data of our spaces. And this paper explores how we're using that data to create predictive models. And at the end, I'll explain how these predictive models feed into a larger vision of autonomous architectural design at the company. So first, a few words on WeWork, and apologies for the corporate jargon. And my colleague Daniel Davis presented here a couple of years ago at Copenhagen, DMS Copenhagen. So apologies for anyone who's familiar with WeWork. I just always assume people aren't. So I'll briefly talk about who WeWork is, what they do, and how our business model demands for this kind of predictive analytics. So WeWork is a global platform for creators. We provide both the physical and digital infrastructure for our members to run their businesses. So we do this through the provision of workspaces and member apps where people can connect. Yes, you can think of it kind of like a Facebook LinkedIn hybrid, and people connect all over the world through our app and through our physical spaces. We currently have over 150,000 members at over 160 locations in 52 cities spread across the globe. And our community consists of entrepreneurs, freelancers, and general creators, as well as larger enterprises, with businesses ranging from Microsoft and MasterCard to small independent branding agencies, lawyers, doctors, and so forth. Each one of our 160 locations has a unique design that attempts to reflect local and community idiosyncrasies. And the challenge then for our in-house architects becomes, how do you create space that satisfies a plethora of needs within a single location? So any one of our buildings may function as brainstorming rooms, breakout spaces, lounges, with work styles ranging from quiet individual focus work to casual group work to private meetings. Central to this experience of a WeWork is our private offices that we offer our members. And private offices at WeWork, can, depending on the context, can take the form of studios, showrooms, company headquarters, depending on the organization that occupies it. And at WeWork, our members lease offices, rent offices on a month-to-month basis. So if a particular office does not satisfy the needs of that member, then they can change office the next month. Therefore, it is vital that our architects get the designs of these offices right prior to construction. Otherwise, offices that are less desirable could sit empty for months at a time. So in this research, we set out to identify the spatial factors and design attributes that influence the success of offices at WeWork, and sought to predict future office utilization based on these attributes. And of course, there are decades of research that go into how office space affects the design of offices affects their inhabitants. Frank Duffy did some work in the early 1970s looking at how the attributes of the physical space of the office affects the organizational design. His early work mapped out how companies' growth patterns, group sizes, and communication strategies and view of the outside world can be hindered or developed by the design of the office and the architectural qualities of the space. And of course, everyone in this room is probably familiar with the work of Ben Hillier and Space Syntax that proposes a variety of analytical methods to quantify physical attributes and the configuration of buildings and urban layouts. So although there's been an abundance of this research throughout the years, there isn't a consensus as to how office space affects inhabitants or utilization. So in this research, we set out to identify spatial factors that influence the success of offices at WeWork. And historically, or to date, these factors were determined anecdotally by designers through rules of thumb. And in this research, we considered whether these factors could be identified empirically using existing data. The population of the study consisted of 34,000 private offices located within 140 WeWork locations. And from this, we took a random sample of 3,276 offices, limiting the sample to 1 to 8 person offices. So WeWork is a vertically integrated company, meaning all of the functionality to source, design, operate, and sell our spaces is in-house. So we have a team of architects, real estate developers, sales team, community team that runs the buildings. And because of all of this, we collect data at every point in our project lifecycle. So what you're seeing on the screen here is before the signing of a lease, before we commit to any building, we go into that building and gather point cloud data. And then on the right is the design of that proposed design of that same building a few months later. And all of this data sits on a centralized Amazon Redshift server. Within the AEC industry, I think this is fairly unique. We have a vast data set of building qualities, and also we collect data on member usage. So with this abundance of data, a big question for our team was what variables do we include in the model, and what metrics should we quantify? So to decide on this, we used a combination of insights from previous research and rules of thumb. So as architects and designers, we kind of assume that everyone loves natural light and views to the outside, so we included whether an office has a window as a metric in our data set. We also assume that people like space, lots of open space, rather than being kind of packed into these dense offices. So what you're seeing here is some of the metrics we quantified. So some of our previous qualitative research found that members don't like long and skinny offices, as it hinders the reconfigurability of the office. It stops them from being able to rearrange desks as they might like. So we came up with a metric to quantify the squareness of each office, which is, of course, the ratio between the width and the height of the office. We also wanted to see if adjacencies played a factor, so whether it matters that an office was next to a bathroom versus next to an office versus next to a lounge space. We also learned from previous research trying to predict meeting room utilization that the distribution of program types in a space affects utilization. So what this chart shows is of all of our locations, the various percentages of program types, are like various percentages of workspaces, circulation spaces, lounge spaces, etc. And so we included these distributions in the model also. We also had assumptions about a building's floor plate and how that relates to the circulation patterns for occupants. So we included a metric for the shape of the floor plate, which is the ratio between floor area and the convex hull of the floor plate, floor boundary. In all, we had over 50 variables we wanted to include in the model. So this is an abbreviated table of those of all the metrics, which range from whether or not an office had a window, to the size of the desk in each office, the floor-to-floor height, the density of the space, which was square footage over desk. And all in all, we had 56 variables. And the target variable, the metric we were trying to predict, was what we call mean occupancy. So as I said earlier, WeWork leases offices on a month-to-month basis. So good offices are constantly leased, whereas bad offices are hard to lease and might be empty for most of the year. To help our designers create desirable offices that are constantly leased, we wanted to predict which offices were likely to be leased and which ones were likely to remain empty. We call this, as I said, mean occupancy, which is the percentage of months a given office was leased. So this histogram shows the distribution of that metric across the sample. And as you can see, the data is highly skewed left, meaning most of our offices are 100% occupied most of the time. And given the non-normal distribution of the data, we decided to kind of create a threshold of trying to predict offices that were below the 35th percentile, which here is below 80% occupancy. So rather than trying to predict a continuous variable, we try to create a binary classification algorithm to identify low-performing offices. So I know everyone, a few people here are familiar with machine learning. So in machine learning, there's a concept called the bias variance trade-off that corresponds with model complexity, where variance is when a model is overly complex, perhaps trained with too many features and overfits the training data and does not generalize well to test data or examples it had not seen before. In contrast, bias is a complete opposite, when a model is not complex enough, underfitting the data, and does not generalize well either. So given the amount of variables we were trying to predict, 56, there was a high chance that we would create, high chance for overfitting, and, to create a model that wouldn't generalize well. So we went through a number of dimensionality reduction procedures trying to arrive at the most influential features. So what you're seeing on the screen here is a correlation matrix where we try to arrive at an independent set of variables among all of the 56 variables we initially looked at. And alongside things like correlation matrix, we also employed the strategy called recursive feature reduction, which using the variable weights from a decision tree classifier, you go through a model iteratively, and at each iteration you take away the least important feature until you arrive at a model that's the most accurate model with the least amount of features. So what you're seeing here is a snapshot of one of the decision tree classifiers, and if we look at the tree of this algorithm intuitively, it kind of validates some of our early assumptions. So in the top left, if you follow kind of this branch here, you can see that if an office has a density above 37 square feet per desk and an aspect ratio above 96%, so meaning an office that has a lot of space and is very close to square, then there's a high chance that office would not be low performing and would be highly occupied. Versus on the right, if you follow the red highlighted branch, if an office is below 37 square feet, if the proportion of glass walls is below 90%, and then again if an office is below 35 square feet per desk, and the proportion of glass walls is below 34%, there's a high chance that office will be low performing, because nobody wants to work in a tight office with no views to the outside and very little daylight. So from the decision tree classifier, we were able to arrive at the 25 most important features, which you're seeing here. In this chart, these 25 features is what we fed into a more kind of complex algorithm, a support vector classifier. But the top 4 features also kind of followed some of our early assumptions. So the algorithm stated that the most important features in determining an office's success were the density of the office, so square feet, ratio of square feet of a desk, its aspect ratio, the squareness, which again was told to us, which we kind of got insights looking at through our qualitative research, the depth of the room, and also the proportion of glass walls. For those who have ever been in a WeWork space will know that all of our offices, our entire floor plate is kind of subdivided with glass partitions, which kind of fits to our brand, but we found through this research that not many people like working in a fishbowl. And we experimented with a number of techniques to classify private offices into those that were low performing, including logistic regression, neural networks, and decision trees. But we settled on a support vector classifier as it proved to be the most accurate. And the great thing about support vector machines in general is that they're very good in working in high-dimensional space with very few training data. Although we had 3,000, like 500 rows, that's still fairly small in terms of the world of like machine learning and big data and artificial intelligence. So this chart shows the algorithm's performance across 10 k-folds with an unseen validation set, and it plots the model's precision and recall. And for those who've done classification before, precision here is, of all the rooms it could have labeled low performing, the percentage that actually were, and recall is of all the rooms in the set that were low performing, the percentage that it actually found. So the model performed significantly better than random guessing, and we were achieving 60 to 70% accuracy and a recall of between 40 and 50% in identifying low-performing rooms. So this is still an ongoing part of the project, but the model's implementation into our design workflow is taking the form of a web service, an API that can be queried within the Revit environment. So this was an effort to enable an efficient feedback loop between design exploration and design validation. So what this image shows is the model's predictions heat mapped onto one of our spaces. So the darker colors are what the model is most confident in will be a low-performing room, and the lighter colors are what will be like high performance. And the idea here is that as designers are laying out the space, they can query the model to see potential performance implications of their design decisions. And getting this kind of intelligence into our product workflow allows our designers to move from a world where they're intuitively anticipating the quality of particular offices to one where they're making informed design decisions based on accurate statistical analysis. So these last few slides, I'd like to end where I kind of began, and this is a bit tongue-in-cheek. So I'd like to take it back to how this work, this predictive modeling, kind of fits into a larger vision of autonomous architectural design at WeWork. And to explain, I'd like to first look at the 5 stages of autonomous vehicles, which have been proposed by some of the larger companies in the space at the moment. And the 5 stages include level 1, where probably at this stage already, where we can automate a single task at a time, like automatic braking. To level 2, where you're automating multiple tasks at a time, perhaps automatic braking along with lighting sensors. To level 3, where perhaps maybe we're starting to grapple with now the handling of dynamic tasks such as parallel parking. To level 4, where you have autonomous vehicles in certain environments, but we still need a human driver to the oversight of a human driver. So to level 5, obviously we're very far away from, to fully autonomous vehicles with no need for a driver. And I think we can think of a similar 5 levels for automation within architecture, where level 1, obviously, I think we've been there for a long time, where we can automate singular tasks of a particular project. So think here of automatic document creation. To level 2, automating multiple tasks at a time. Think of here about generative geometry coupled with some environmental analysis. In level 3, where I think we're starting to kind of get into at WeWork and obviously in the larger AEC industry, the handling of dynamic tasks within the design process. And here, we can think of the evaluation of design decisions, which up until this point have been done by human designers, but I think with the advent of deep learning, we can start to get into more offset this with machine intelligence. Level 4, the autonomous design of architecture within certain specific building typologies. And I say specific typologies because I think if the metrics of that typology are clear and the designs are pretty consistent from project to project, we can probably start to automate the design of those projects. To level 5, which I think we're a long way off to obviously automated architectural design without the need for human intervention. And I think level 4 and level 3 is where we're starting to get to a WeWork because our success metrics are clear. We're trying to maximize the experience of our members and also trying to kind of increase occupancy. So we have clear success metrics and our designs are pretty consistent. It's workplaces. So our designs are pretty consistent from project to project. So I think what this project is trying to get to is that the predictive modeling can kind of offset some generative layouts of our spaces, and perhaps next time this conference is on, we'll be talking about level 4 automation. Thank you.
Thank you. I think that's a pretty straightforward thing you're saying here. So rather than questions, I would ask, is there any reactions from the public? There's a mic, maybe.
So thank you. This is very interesting. I have one question. Is there something that the program made you discover that you were not suspecting? Like, because most of the things you presented sounded like a confirmation of intuitions, like people like natural light, etc. Did you discover something like completely that you would not have guessed was it not for this project? And I also have a second question. Is this only an in-house project? Like, do you consider this project as kind of competitive advantage of WeWork, like something you developed for? Because I mean, you're a private business, so is this something you developed for efficiency, or will these be published, shared, and like, what's the status of this project? Thank you.
Cool. Great question. So to answer your first point, yes, absolutely. There was many aspects we kind of were surprised about. So the features that were the algorithm decided were the most important. So we assumed that people like natural light, but actually the metric that said whether an office had a window or not did not appear in the final 25 features. And actually also one of the features was the wall types of each office, and that was kind of a surprise because we found that people actually don't like having glass partitions in their offices. So there definitely were a few surprises. To your second point, well, the paper's published, so it's in the public domain. And yes, I mean, I work for WeWork, it's a corporate company, it's obviously for profit, so absolutely this is for to gain some kind of competitive advantage. Yeah.
Thank you.
Any other questions or remarks? Yeah.
Are you an architect?
Yeah, by training.
Okay. It's just, you start out saying sorry for the corporate jargon, and you're moving towards the corporate idealized ambition for architecture. How does that make you feel? It's a very technical question.
To me, the work's interesting, so I'm fine with it. How do you feel?
No, I see it from a technical perspective. That's for sure.
Yeah.
But do you see that that is the true ambition of architecture? To move towards full autonomy and corporate idealization?
Yes and no. I think, as I said, for specific building typologies, hospitals, retail, office space, I think we could start to automate a lot of aspects of those projects. I think I'm going back to what Sophie said yesterday. I think certain things, just because we can do it doesn't mean we should do it. But I think it's an interesting problem. These are interesting problems to solve anyway. And for sure, I think if we have consistent metrics across typologies and consistent designs, building codes and whatever, then I think we could automate a lot of aspects of architectural design within specific typologies.
I think there's a very interesting discussion to be done still, but we're going to go to the next speaker. Thank you very much, Carlo.